Hi, well, this is reading quiz number 18. This is where we get to put all of it together, all these derivative rules that we've learned, all these derivatives of common functions that we've learned. It all comes together, and our first investigation is how does the derivative affect the graph of a function? So we're going to start with the first derivative. Well, one reason that we take all these derivatives is that it tells us a little bit about what the graph of a function looks like. So remember pre-calculus when we talked about increasing and decreasing functions? Let's go back to our definitions and the fact that we defined f prime of x sub 1 as the limit of x, as x2 goes to x1 of f of x sub 2 minus f of x sub 1 over x2 minus x1. Well, this derivative gives us a clue as to how we can relate that to increasing and decreasing behavior of a function. First of all, if you remember, an increasing function is one where the function values are getting higher as the x values increase. So our formal definition will be that if x sub 1 is less than x sub 2, then f of x sub 1 is less than f of x sub 2. If you go back to our definition up here, our limit definition of our derivative, we can see that that'll mean our numerator will be positive because f of x sub 1 is less than f of x sub 2. And our denominator will also be positive. X sub 2 minus x sub 1 is going to be bigger than 0. So that'll mean, overall, since our numerator and denominator are both positive, our function will be increasing if f prime is bigger than 0. If the slope is positive. A function is decreasing, on the other hand, if x sub 1 is less than x sub 2, means that f of x sub 1 is bigger than f of x sub 2. In other words, the function values go down as our x increases. Some more definitions that will be helpful. A critical point is a point where f prime of x is equal to 0, or f prime of x is undefined. We will be using the term critical point a lot here. A particular type of critical point is what's called a stationary point, and that specifically is where f prime is equal to 0. Another definition we'll encounter is monotonic. A function is monotonic on an interval if that function does nothing but increase or does nothing but decrease on that interval. So let's take a look at some examples here. Suppose that f of x is equal to x to the fourth minus 4x cubed plus 4x squared. Find where f of x is increasing and where f of x is decreasing. Well, as we just learned, it'll be helpful to find the first derivative, because if the first derivative is positive, we know that f is increasing. And if the first derivative is negative, f of x is decreasing. So when we take the derivative, we get f prime is equal to 4x cubed minus 12x squared plus 8x. Then we need to find any critical points by finding where the derivative is 0 or is undefined. And the reason why we're finding critical points is we want to find where the derivative is positive or where the derivative is negative. Well, at some point, either the derivative has to be equal to 0 or is undefined if the derivative is going to go from negative to positive or from positive to negative. So our critical points are our transition points. This brings us back to our wonderful days of algebra. We can factor out a 4x, and we're left with x squared minus 3x plus 2. Continuing to factor, we get 4x times x minus 2 times x minus 1, which gives us 3 critical points, x equal to 0, x equal to 1, and x is equal to 2. Now, we're going to use this tool that's called a sign test on the derivative to help our analysis. Place any critical numbers, in this case 0, 1, and 2, on the top. And what we're testing is the sign of the first derivative. Is the first derivative positive or is the first derivative negative? Okay, so our first check will be to check a number less than 0. If the derivative is less than 0, if x is less than 0, is our derivative less than 0 or bigger than 0? So a number you might choose is negative 1. After a while, you won't need to choose a number. You'll start to see patterns in this. So when we choose negative 1, we get 4 times negative 1, which is a negative number. Negative 1 minus 2, which is also negative. and negative 1 minus 1, which is also negative. So we have three negatives. Three negatives multiplied by each other will give us overall a negative. And we put that to the left of 0. So now we try a number between 0 and 1. Let's try 1/2. 4 times 1/2 is positive. 1/2 minus 2 is negative. 1/2 minus 1 is negative. Two negatives make a positive. A number between 1 and 2. 4 times 1.5 is positive. 1.5 minus 2 is negative. 1.5 minus 1 is positive. We have one negative. That'll give us a negative overall. A number bigger than 2. Let's say 3. If x is equal to 3, we get 4 times 3, which is positive. 3 minus 2, positive. 3 minus 1, also positive. All positive gives us a positive. I want you to notice a pattern here. We get negative, positive, negative, positive. If you notice, our derivative is a cubic. Well, what's the end behavior of a cubic? As x goes to negative infinity, our function also goes to negative infinity. In this case, our derivative goes to negative infinity. As x goes to positive infinity, our derivative will go to positive infinity. So it makes sense that we've got a negative on the far left and a positive on the far right. In between, if you remember, we had a term in precalculus called multiplicity. And what our multiplicity told us is whether or not we cross the axis. All of our roots that are given all have a multiplicity of 1, which means that we're going to cross the axis at every single one of our roots. Therefore, we get this pattern going from negative to positive to negative to positive. We'll see in just a minute a situation where we don't necessarily go negative to positive to negative to positive. So let's put this all together. The question asks, where's f increasing and decreasing? F is increasing wherever f prime is bigger than 0. As we can see, that would be from 0 to 1 and from 2 to infinity. F is decreasing wherever f prime is less than 0. This was from negative infinity to 0 and from 1 to 2. Put it all together, we will talk later about how to put a graph together, but basically we're decreasing all the way up to 0, and then from 1 to 2, and then we're increasing from 0 to 1 and from 2 to infinity. Let's try another example. Suppose f of x is equal to x squared minus 1 over x cubed. Find where f of x is increasing and decreasing. Again, we need to find the first derivative. This is where the quotient rule comes in handy. And I've done a little simplifying here. Got down to 3x squared minus x to the 4th over x to the 6th. We want to find any critical points by finding where the derivative is 0 or is undefined. So f prime is equal to 0 when the numerator is 0 but denominator is not. That would be when x is equal to plus or minus root 3. F prime is undefined when denominator is equal to 0. In this case, when x is equal to 0, it just so happens that the numerator is equal to 0 there as well. It's still going to be a critical point. We're going to use our sign test. We've got our three critical points, negative root 3, 0, and root 3. Don't forget about that 0. A lot of people tend to forget our critical points when f prime is undefined. We do a quick sign test. All right. In this case, we've got our derivative right here. We can test a large negative number. When we do so, we're going to get a large negative number on the top and a positive number on the bottom because this is x to the 6th. Overall, we get negative. Similar tests will show us that we get negative, positive, positive, negative. Notice what we've got going on at 0. At 0, we don't have a sign change in our derivative. And the reason for this has to do with the multiplicity of our roots. If we were to factor out an x squared and canceled, we would still get an x to the 4th in our denominator. That x to the 4th is an even power, right, which indicates to us that we are not going to be changing our sign around x is equal to 0. And we'll see why on the next slide. F is increasing wherever f prime is bigger than 0. As we just saw, based on our sign test, that happens on the interval negative root 3 to 0 and 0 to root 3. F is decreasing whenever f prime is less than 0, which happens from negative infinity to negative root 3 and from root 3 to infinity. And note what was really going on at x is equal to 0. If we remember our original, we would note that f has a vertical asymptote at x is equal to 0. Another example, this one involves trig. Suppose f of x is equal to x plus 2 sine of x. Find where f of x is increasing and where f of x is decreasing on the interval only from 0 to 2 pi included. Again, we find the first derivative, which is 1 plus 2 cosine of x. Find our critical points where the derivative equals 0 or is undefined. All right, so if you remember from your trig, we need to isolate the trig function. We get cosine of x equals negative 1/2. And we're only concerned about 0 to 2 pi. In this case, you might have to expand your answers if we have a different interval later on. Cosine of x is equal to negative 1/2 only at 2 pi over 3 and 4 pi over 3 on this interval. And now we do a sign test on the derivative. Notice I included 0 and 2 pi, which are our two endpoints. It helps lock in what our sign test is testing. And we take a look. We take numbers between 0 and 2 pi over 3. Let's say pi over 3. It doesn't matter. The derivative is going to be positive in that region. A number between 2 pi over 3 and 4 pi over 3, let's say pi, we're going to get a negative derivative, and then we get a positive. And that has to do with the nature of the trig function. So finishing it off, f is increasing wherever f prime is bigger than 0, which happens from 0 to 2 pi over 3, with 0 included technically. And then from 4 pi over 3 to 2 pi, the reason why we include our endpoints here is because the derivative is actually bigger than 0 at each of those points. The derivative is equal to 0 at each of these interior points, 2 pi over 3 and 4 pi over 3. F is decreasing from 2 pi over 3 to 4 pi over 3 because the derivative is equal to 0. And you can see from the graph of this function how those intervals correspond to our graph. Another example here from the reading. Suppose f of x is equal to x to the 1/3 times x plus 3, which looks like a really complicated function. Find where f of x is increasing and decreasing. We take the first derivative, which is 4/3 x to the 1/3 plus x to the negative 2/3. And I will point out that I did distribute the x to the 1/3, making sure to add our exponents whenever you distribute here because you have a common base. One of the tricks that you're going to use to find critical points here is to always factor out the lowest power, meaning the most negative one. In this case, the lowest power is the x to the negative 2/3. When I factor that out, I'm left with a 4/3 times x. And the reason why you got to think of this as an x to the first. Well, if you're going to go back and redistribute, you've got an x to the first times an x to the negative 2/3, which brings you back to your x to the 1/3. Another way of looking at it is we could just say, all right, 1/3 minus negative 2/3, taking away that power, would leave us with a 1 here. And of course, it leaves us with a plus 1 when we factor out an x to the negative 2/3 here. You got to be very careful here. You want to find your critical points where f prime is both undefined and where your derivative is equal to 0. We have an undefined issue because x to the negative 2/3 is 1 over cube root of x squared. That 1 over part gives us a problem with our denominator when x is equal to 0. That's a divide by 0 error. So we have a critical point at 0, and then a critical point when you solve this algebraic expression and set it equal to 0, we get x is equal to negative 3/4. A quick sign test on the derivative. And I should say it's always helpful to factor out the derivative before you do a sign test because it's easier to see where the patterns are. In this case, we take a number that's less than negative 3/4, like let's say negative 5 million. Well, negative 5 million to the negative 2/3 is going to be a positive number because we've got that squared there. And we get a negative 5 million to times 4/3 plus 1. And sorry about that. I had an error in my sign test. It should go negative, positive, positive, all right, when you do your test. And we can therefore conclude from that f is increasing where f prime is bigger than 0, which happens from negative 3/4 to 0, and then from 0 to infinity, and decreasing whenever f prime is less than 0 from negative infinity to negative 3/4. There's the graph. It does have a vertical tangent at x is equal to 0.